Thanks everybody for being here. I'm Maxine Xin from UT Austin, and today I'll be talking about TacMineR, a tool that we built to do automated discovery of tactic libraries for indirect theorem proving. So to get us started, I assume everyone here is relatively familiar with the notion of indirect theorem provers, ITPs. So there are a variety of ITPs being invented in the past decades, and they are widely used across the different domains, ranging from software and hardware verification, mathematics, cryptography, and many others. So I hope we all agree on sort of how important ITPs are, so let's talk more about them. One very important thing is how do we write proofs in them, right? And as I'm sure many of you here already know, the core building blocks in ITPs are tactics. So a tactic can be seen as an action we can make to do a one-step transformation to the proof state. For example, we can say introduce a variable to the context, or to rewrite the goal using some lemmas. And then we can use these tactics to gradually transform and simplify our proof goals until all the proof obligations are discharged. So great, these tactics are quite powerful. But unfortunately, most of these tactics, one tactic can only make a very small step transformation. So when the theorem gets really complex, the proof can get very low level and very verbose, so it becomes very hard to read. So to address this problem, many people write their own domain-specific custom tactics that they can use to make proofs more readable, more concise, and more reusable. And precisely because of that, people routinely write such custom tactics and package them into reusable libraries such as mathlib in Lean for mathematical proofs, or Flock library in Coq for floating points. So this brings us to our central question, which is, wouldn't it be really nice if we can automatically learn such tactic libraries? In my opinion, this has a few benefits. So first, we can discover common proof patterns and motifs. And then we can use these patterns or abstractions to help with proof automation. As the abstractions that enable larger transformations can reduce the proof search space by a lot. Also, we can use them to facilitate a form of lifelong learning where we can continuously enrich the prover with new tactics and make the system steadily more capable over time. So in order to achieve all these really nice things listed here, we created a tool called TacMineR, which can automatically discover tactics from a given proof corpus, which means a set of proofs. So specifically, TacMineR takes a proof corpus and would output a tactic library that maximally compress the proof corpus. Furthermore, TacMineR can also be used to refactor these existing proofs using the extracted tactic library. Okay, so now we have a big picture on what TacMineR does and how it works. Let's actually break it down to talk about how we achieve the tasks. So for the remaining of the talk, I'm going to first talk about how to refactor proofs in a principled way, and then I'll be talking about how to detect common patterns that can be extracted as tactics and packaged into libraries. So let's first talk about the proof refactoring procedure. So the problem we're trying to solve here is given a custom tactic and a proof that can be refactored by the tactic. How do we exactly detect this and actually replace the corresponding proof text with the custom tactic? So one might think here, how about we just do it syntactically, right? So what that means is just given a custom tactic containing a sequence of atomic tactics in the tactic body, we can search if the same sequence of atomic tactics exists in the proof text modulo the tactic arguments. And if that exists, we can try to unify the custom tactic with the corresponding proof section by searching for the correct argument bindings. And if such search exists, then we can replace the proof text with texts with the custom tactic with the correct argument binding. However, TacMineR here doesn't necessarily agree with this approach, as we think this approach is too brittle and would actually miss many refactoring opportunities. For example, here's a counterexample. We can see that all the atomic tactics appearing in the body of the custom tactics actually are present in the proof below. But the problem is they are disconnected. We can see the yellow parts are disconnected, the green parts are disconnected. So when this happens, the previous syntactic approach would actually fail. So this poses our first challenge. How can we capture beyond just the brittle syntactic relationships? So basically, we need a different refactoring approach. So for this purpose, we introduce tactic dependency graph, TDGs, which are intended to capture the deeper semantics, the logical dependencies among tactics. And now I'll explain what its constructs are. So here, a node represents a tactic application. A tactic node would have its formal input and formal output decided by Rocq's built-in semantics. And here, an edge would represent the dependencies between tactic applications. More specifically, an edge from tactic A to B, labeled from X, Y, indicates that the formal output X of A becomes the formal input Y of B. So yeah, because the TDGs can represent much more beyond just syntactic relationship, one TDG can actually represent very different proofs. For example, I have two proofs here which have the exact same atomic tactics but in very different orders. But both of them can actually be represented by the same TDG here. Okay, so clearly, clearly I hope we all understand what TDGs are and how they work right now. So let's actually talk about how do we refactor the proofs using our TDGs. It's actually pretty straightforward. So given a Rocq scripts, we just first convert it into the TDG representation, of course, and then we find isomorphic subgraphs in the proof TDG that corresponds to the tactic TDG, which are the highlighted parts over there. And then we, to actually do the refactoring, we just create two new nodes representing the custom tactics. And then we replace the corresponding subgraphs with the newly created node while maintaining the incoming and outgoing dependencies. OK, cool. So yeah, sorry. And then we can just use topological source to convert the refactored TDGs into the Rocq scripts. So now that we understand how the refactoring procedure works, the tactic learning procedure actually follows pretty intuitively. So given a proof corpus, we just we just try to find their common isomorphic subgraphs. And that will give us our extracted tactic. So I know some of you might be thinking like, OK, this is conceptually straightforward. But how about in execution, since as we all know, finding isomorphic subgraphs is hard. And so for that, we used a graph enumeration technique, where the enumeration is guided by its input and also enhanced with some pruning techniques, which made the enumeration computationally feasible. I'm not going to talk about the details here, but please refer to our paper if you're interested. OK, so now we have understand both of the procedure. Let's actually chain them together to get the big picture. So given a set of proof corpus, we will first just extract the tactic that maximizes our defined objective, here the compression ratio, and then we can refactor the proofs using this extracted tactic. And then we can repeat this procedure until no further tactics can be found, which means no further common subgraphs can be found. And the output will be our tactic library. And to understand how our work did, we want to know how well can TacMineR extract libraries from existing proofs, and if learned tactics help with proof automation. And since this is time limit, I'm just kind of quickly say we compare with the syntactic approach that a tool called Peano we talked about earlier, and we have gathered proofs from these different domains. We compared, we have two results for the first research question. The first one is on the statistics of the tactics we extracted. We can see that TacMineR learns 3 times of the tactic learned by Peano and are much more frequently used as well. And they also achieve much higher compression rate. So our first conclusion is that TacMineR learns 3 times tactic compared to Peano, which the baseline, and reduces the corpus size by 26%, while Peano only does it by 9%. OK, and our secondary experiment is on proof automation. So we want to see how our tactics help improve with the proof automation results. For the proof automation tool, we chose Copra, which is one of the state-of-art for automation tool it's LLM assisted with compiler feedback. And in this experiment, we compare the proof automation results between the out-of-box Copra with the Copra with Peano and TacMineR extracted tactics. And what that means is just like we give Copra the information about the custom tactics it can use and how to use them. OK, cool. Yeah, if you have any questions, and Maxine, feel free to talk to me after the talk.
Yeah, and let's say